Hi, my name's Ian Brooks. I'm a professor in the School of Earth and Environment at the University of Leeds, and I'm participating in the MOSAiC campaign in the Central Arctic as part of the atmospheric science team. So MOSAiC is a huge international collaboration that is studying the various physical, chemical and biological processes that are part of the climate system controlling Arctic climate. And it's based around an icebreaker, German research ship called the Polarstern, which is being frozen into the sea ice in the Central Arctic Ocean and will be left to drift with the ice for a full year. So the reason we need to study the Arctic is that it is a region of great sensitivity to climate change. It's warming approximately twice as fast as the Earth as a whole is warming. And some of the most visible manifestations of that are dramatic reduction in sea ice extent. We see every year the sea ice minimum is getting smaller and smaller. Participating in MOSAiC is a fantastic opportunity to do research in a really remote environment that's difficult to get to, difficult to work in. It's particularly exciting to be able to make measurements over a full year. I've worked on 4 previous research cruises in the Arctic, but they've all been summer-only expeditions, so 1 or 2 months in the sea ice during July, August, September. So I'll be going out on the initial part of the MOSAiC expedition to install the instruments in a couple of weeks' time and coming back at the end of October at the start of winter. I then get to go out again in January in the depths of winter where it will be 24 hours of darkness, and we'll get to see the first sunrise sometime in March and come out just as spring is starting in the middle of April. Undertaking research in the Arctic is a really difficult challenge. It needs a lot of logistical support, it's expensive to do, and it requires a lot of teamwork. MOSAiC is on a scale where that applies much more perhaps than on any previous projects I've been involved in. It's absolutely huge collaboration. There are more than 600 scientists who will pass through the field site on the Polarstern. There are I don't know how many countries participating. There are support ships from Russia, Sweden and China who will be transferring science teams in and out from the Polarstern as we change crews every 2 months. It's inherently very collaborative science. None of us can use our measurements completely in isolation. We need to work with other teams. My measurements of boundary layer dynamics will be important to the groups that are working directly on cloud microphysical processes, to the teams that are looking at sea ice deformation because the wind stress at the surface is what moves the ice around. So we're all working very, very closely with each other in ways that perhaps we haven't thought of yet, that once we have some measurements, somebody else will see those and go, oh, I could use those, and a new collaboration will be born. That's part of the excitement of doing science like this, that there are so many different applications for the measurements that sometimes we had never thought of when we went out to make them. The huge scale of MOSAiC enables us to make measurements over the full calendar year. And this has only been attempted once or twice before and on much smaller scales in terms of the range of measurements that are being made. The reason we want to make measurements over the course of a full year is because we need to understand the processes throughout a full calendar cycle of how the Arctic climate works, how the ice forms, how it melts during the summer. We can't build a climate model that properly represents all these processes if we don't understand them. And the only way we can gain the understanding we need is to go out there and make the measurements throughout the full year. The measurements that I am making are of the dynamics of the lower atmosphere. That's the bit called the boundary layer that is between the surface and maybe 500 meters to a kilometer in depth. And this is the bit of the atmosphere that interacts directly with the surface through turbulence. So it's chaotic mixing of the air. It's driven in part by mechanical mixing from friction at the surface. The boundary layer is important, or turbulent processes within the boundary layer are important, because they control the exchange of heat, trace gases, water vapor, aerosol particles between the surface and the atmosphere. And many of these are factors which influence the properties of clouds. And so we need to be able to represent the boundary layer correctly in order to represent clouds correctly within models. The boundary layer in the Arctic is often very shallow. It often has properties that are a little different from those in mid-latitudes, and some of those properties are not reproduced in any current models. The research team at Leeds consists of myself, and at the NCAS Atmospheric Measurement Facility, Barbara Brooks and Ryan Neely. AMF are providing the LiDAR systems that we're using. These are very expensive instruments. They're difficult for individual research groups to buy, so AMF provides a service to the whole UK atmospheric science community, enabling us access to specialised instrumentation that we might not be able to afford on our own. I've worked with AMF on 2 previous Arctic research campaigns where they've provided both the LiDAR that we are using this time and other instruments for shorter term cruises of about a month or 2. So the measurements that my team are making are of the mean wind profile from the surface up to an altitude of maybe 1 kilometre, and the turbulent dynamics of the boundary layer. And we're measuring these primarily with remote sensing measurements. We have 3 different instrumentation systems that are going out. The first instrument we're putting out is a wind profiling LiDAR. This will sit on the upper deck of the Polarstern and make continuous measurements of the wind profile from close to the surface up to a kilometre or so. We'll get a complete wind profile measurement about every 5 or 10 minutes for the full year. The second instrument we're putting out is another LiDAR, which will also make wind measurements, but this one is sitting out on the sea ice about 500 metres from the ship, and it is going to make measurements in coordination with a second identical system that is operated by collaborators of ours from the University of Trier in Germany. And we'll use the 2 LiDARs together to look at the same volume of air. And by using various different scan patterns of the 2 LiDARs together, we can make measurements of the vertical structure of the turbulence dynamics within the atmosphere. So the third instrument we're deploying is a Doppler SODAR. This uses bursts of sound and listens for the reflected or echo of that sound. The acoustic pulse is reflected from density gradients in the air, which are mostly a result of gradients in temperature on small scales of just a few centimetres, 10 centimetres or so. In addition to those 3 remote sensing instruments, we're also deploying a 30-metre tall mast, which will have instrumentation right at the top of it that makes direct measurements of the turbulence properties of the atmosphere.